right, recording is rolling. We're a few minutes into Friday, December 3rd. So, anybody figure this out yet? What the tension is? Right. Tell you what, I'll take you guys through how to solve this the way I've been showing you. And there's actually a shortcut to answering this that I'll show you after this traditional way. So, you guys remember, this is all in equilibrium. In fact, you see it right here, hanging from the ceiling. So, equilibrium. We're looking at these two conditions. The sum of the forces in each direction has to be 0 newtons. And, well, in this case, it's just the y direction because there's just vertical forces, right? 1 down and 2 up. Okay. So we'd be in the y direction. And also the sum of the torque has to be 0. And this would be Newton meters, right? Right. So the first condition, the sum of the forces has to be 0. From that, you can say, well, the force down is 10 newtons, so the two tensions up have to add up to 10 newtons, right? So that it all zeroes out, right? But that by itself isn't enough to solve it. But the second condition, well, this is the one we're going to use to actually nail this thing. So you have to pick a pivot point to sum the torque about. And one thing that I was trying to get have you guys get out of the lab a couple days back is that you can really pick any point as the pivot point, and mathematically it works out. But let's pick this point right here. And the reason I really like this point is because the fact that one of the strings is at that point means that the force from that string doesn't cause any torque about that point itself. Like if you push on the hinges of the door, it'll never rotate the door. And that takes two unknown values. And then when we set this equation, it'll narrow it down to only one unknown value, which would just be the tension in the other string, because this one's just going to zero out, right? So let's do that. You guys remember, of course, torque is R cross F, right? Radial arm crossed with the force. So we're going to add up, like the sum of, right? We're going to add up the two other torque values, right, relative to this pivot point. So do you guys see how the lab weight is trying to cause a clockwise torque and the string is holding back counterclockwise? Okay, that? So we've got this radial value of 90 centimeters. So R cross F, right? Got 90 centimeters crossed with a 10 Newton force, right, which is plus at 100 centimeters from that pivot point, right? 100 centimeters, radial arm. There is the tension in the right string. Okay? I'll call it T sub R, like tension in the right side. Okay? And that torque has to sum to 0 Newton, well, Newton centimeters in this case, right? Newton centimeters. That has to go to 0. Is that okay? Okay, so a couple of algebra steps to get to the answer. You're going to subtract this over, these 900 Newton centimeters, and then after that, divide by this 100 centimeters. So that'll give you tension on the right side is 900 Newton centimeters, and it would be negative, right? Subtract it over. Right? Divided by 100 centimeters. You guys see how that? Okay. Centimeters cancels, hundreds cancel. Okay. And the tension on the right side is negative 9 newtons. Okay, so the magnitude is 9 newtons, and the negative sign just means that it's in the opposite direction of the weight, because looks like the way I've defined this is down is positive, so up has to be negative, right? Is that? You know what? I forget if I mentioned this or not, but when you guys were doing that torque lab a couple days back, if you wanted all your numbers to work out right, then when you were recording forces, you did have to consider that the spring scales were pulling up and the weights were pulling down. Okay, so like if you miss that detail in your numbers, then if your numbers were like totally not making any sense, that could have been one of the reasons why. Yeah, so directions of these things matter. Right? Now, if this is, well, has a magnitude of 9 newtons tension, what's the magnitude of this guy? How many newtons of tension? 1. Yeah, because of, very quickly, this other condition, that the forces have to sum to 0. So if it's 10 down, it has to be 10 total up. So 9 plus 1 would be 10. Right? Is that? Right. So, yeah, so tension on the left side would be negative 1. Okay. Right, so I did tell you guys that there was a shortcut to this too. Right? Here's the shortcut to this type problem. Do you guys see how this weight is 90% of the way over to the right? And it turns out that this tension on the right side is also carrying 90% of the total weight, right? So wherever this is proportionally on the meter stick, the one that it's closer to is going to carry more of the weight. It's going to carry that proportional to where it's located. For example, if this is right in the middle, you guys know the weight is split 50-50, right? And if it's all the way on the right side, then wouldn't the string pretty much be holding 100% of that weight? Pretty much. All right. So here's that. You know what? Thinking, do I want to? Yeah. Let's go on to types of equilibrium. Okay, so types of equilibrium. Thinking there's some more stuff I want to tell you guys, but we got a short day, so we have to save some stuff for next week. Yeah, I guess we got some more days coming up. Okay, so tell you guys about stable, unstable, and neutral equilibrium. Okay, so give you guys some physics definitions of these things. Okay, because you guys should probably know something stable or unstable already, but what's where like the physics definition? Okay. So if something is stable, then any motion will raise its center mass. Okay. If something's unstable, then any motion will lower the center mass. Okay. And if it's neutral, then any motion will neither raise nor lower the center mass. Okay. And so give you guys some pictures to go with those word definitions. So they got some floors. And first floor, I'm going to park this pyramid shape. Okay. Center mass right there. Okay. Second picture, well, I'm going to take that pyramid and turn it upside down. Like this. And here's the center mass. Okay. And third picture, let's go with like a baseball. Center mass right there. Okay. So marked out center mass with a point. Okay. Now, I guess even if before I gave you guys all these definitions, you can say, well, it looks like this picture on the left is going to be stable, and this picture in the middle is going to be unstable, right? And that would be true. So this is stable and unstable. But let's see how this pairs with these definitions. So motion would raise the center mass for stable. Right. Here, what if I do this? What if I come along and I push the top point of this and it starts pivoting around this left point? Hey, maybe like causing a torque, right? This thing starts to rotate. Couldn't it rotate sort of like this? You could imagine that animation is like rotating. And that would move the center mass up here a little bit. Right. Or what if I push it this way and it rotate around this right point? So that might send it more like this type motion, right? And center mass would move like up here, right? But you see, like either way you push it and it rotates, its center mass would have to raise. Right? No, not forever. It would eventually come back down and land on the other side. But that initial motion would raise it. Now, things tend to want to roll downhill. Water wants to flow downhill. And same thing here. The center mass thing is already in its lowest position. So any motion, it's kind of like trying to do something uphill, like try to raise it. In fact, you can actually use that height change of its center mass to calculate the work done during that rotation, right? Because that would take some force times distance, but how many joules of energy? Well, if you knew that height change, you could say the mass of this thing times the gravity field times that height change. You could calculate that, maybe do some geometry. That would represent the number of joules to rotate that thing. Okay. Now, unstable, see the center mass is right over, it's supposed to be, I didn't draw it super well. Okay. It's supposed to be right over that single point of support. But if you tip it any little bit, I mean, it's kind of like trying to balance a pen on your finger, which is like nearly impossible to do. Okay? You see its mass would have to lower, right? Like if it starts to rotate, let's say you push it to the left a little bit, goes down like that, push it to the right a little bit, go down sort of like this, right? Either way, its center mass would have to move down, right? Which would, that would just make it unstable because it would want to do that. Okay? What about this baseball? This baseball also has only a single point of support, and its center mass is over that single point of support. Right? So that's true. Right? But if you push, just gave it a little push to the left, a little push to the right, wouldn't center mass just also go parallel to the ground, like roll parallel to the ground, which would mean that it doesn't raise or lower. So this is considered to be neutral equilibrium. Okay. All right. All right. How about those are some pretty basic examples. What if you do something like this? What if you have like a roof and you park a baseball on top of a roof? So its center mass is also over just a single point. Right? What do you guys think that's considered to be? You're saying unstable? Yeah, unstable because tips any a little bit and the center mass would have to lower. Okay, so that would be unstable. How about if you have a picture frame? And maybe this is transparent, you're looking through the other side. Here's a nail on the wall. Here's a string that's holding up the picture frame. Here's the center mass of the picture, right? Okay. Now, this one, I'm showing you guys that from the point of support to the center mass is actually below that point of support. Okay. Let me see, show of hands what you guys would think for this. Is this stable, unstable, or neutral? How many of you guys think that this is considered stable? Stable. Yeah, okay, so you guys are all saying that's true, stable. Okay. And then from our definition point of view, you see if you give it a push, it's gonna rotate about this nail, right? Like that could be the pivot point, and its center mass would have to raise it that way, or if you push it to the right, have to raise it this way. And imagine this animation, it's sort of like rotating about that nail. Okay. So it's already in the lowest position that it's gonna be, so yeah, that would be stable. Right. Let me throw one to you that tripped up my last class. I wonder if you guys are going to get this one. What about that right there? So here's the floor. So show of hands. How many think that this is considered to be stable? Who says stable? Who says unstable? Okay. And who says neutral? Okay. So let's think about what happened. Say if I push this thing this way and it starts pivoting about this point right here. When this thing rotate kind of like this sort of, right, something like that. Okay. And then the center mass actually would go up a little bit, wouldn't it? Have to go up a little bit. Okay. And then vice versa, if I push it to the right and it rotates a little bit about this point, and it looks something kind of like this. Okay. Now, it's not a huge distance that its center mass would raise, but it would have to raise a little bit before it would go back down. Okay. So it's sort of like in a valley at the top of a mountain, but it's already at a sort of like low point locally. So this is considered to be stable. It would be stable. Okay. Maybe that make you think something about this base of support. That's what this is right here. This is a base of support. Okay. Now, in a few minutes, I'm going to have you guys up moving around the room. And so when you are, you might want to try this next demo that I'll show you guys. Suppose you have a floor and a wall. Okay. You guys ever tried this to put your back against the wall and reach down and touch your shoes? Let's say you have your feet also against the back of the wall. Okay. And you try to reach down and touch the tip of your shoes. You guys ever tried to do that? Okay. Here, let me demo this real fast. So like this. Okay. So got my heels against the wall. Okay. Try to reach down. Okay. Really hard to do. Now a few people could do it, but not too many. So I don't know how many here could do this. And the physics of this is like this. The area of your shoes is like a base of support. This is a base of support. Okay. So your center mass is pretty much like at your belly button, like somewhere there. Right? And when you reach down, now part of the catch of this that makes it really hard is the fact that your back is against the wall. No part of you can really move backward, right? It's sort of like locked in place, right? But your head is moving forward. So your center mass is overall going to shift like in that forward direction, like that way. And once your center mass crosses this line right here, once it goes beyond the base of support, like say like goes out here, well, that would make you unstable and you're just gonna fall over, something like that. Right? suppose I got, say I take this pin and I threw it through the air. And it's all like rotating and it's flying through the air. Now, you guys remember projectiles follow, what kind of path? What kind of shape is that? Yeah, parabola. They're gonna follow a parabola path, right? Right. But let's say we're watching this thing rotate. So it's spinning. So like try to draw this thing sort of spinning. It's like spinning through the air as it's going. Something like that. There actually is one single point that actually would follow that parabola path, and that's the center of mass. Only the center of mass does, right? Which is, center mass is also the point that it'll bounce on your finger. So, it's like right about there, right? So that point would. Now, the ends of the pin, they're going to be like doing all kinds of crazy rotation motion, but the center mass, that would actually follow the straight parabola path. What about this? What if I have like a weird shape like a wrench? Has a lot of mass on this end and something like that. And maybe its center mass is probably right about here-ish, right? That could be like the point you could balance it on your finger, something like that, right? And I have this wrench on an air hockey table surface. So you guys imagine an air hockey table. I take it and go, and I fly it across the surface, and it starts rotating as it's like moving forward, right? So say it's moving sort of like in this direction on this air hockey table. Something like this, like V. Okay? But the endpoints are all like spinning all crazy. Okay? What about the center mass? Do you think the center mass actually does follow a straight line going across that air hockey table? Show of hands, how many guys think it does? How many guys think the center mass actually would follow a straight line? Yeah, you're right, it would. Right? And that would actually be the only point that would be following a straight line. Like if you, let's say you attach a little LED light right here and then turn off the lights and just follow that LED light, you go like super like crazy spirals. But the center mass, yeah, that actually would follow a straight line. Okay. Let's do a center mass activity. So back on my lab tables, I've got a bunch of foam board cutouts. This is one of them. Okay. This one's labeled number 9, and then there's 9 altogether. So this is the last piece. Okay. And we're gonna do like a multiple choice type activity. Do you guys see that quarter page on your desk? That blank quarter page? So write your name on that blank quarter page and number it 1 through 9. Got your name on that blank quarter page and number 1 through 9. Okay. All right, so there'd be multiple choice. Hey, I wonder which of these points is the center mass of this like weird foam board cutout shape. Okay. Well, I know there are a few ways you can find this. Right? One way you can do it is it's any point that so I can set this up sort of for the camera. Okay. Here, I've got this string. Okay. The string with the nut on it and a binder clip. Okay. If I clip this, say to an itch, okay, and just let the string hang down. Okay. Let me show you guys what this is gonna look like. Straight. Reflip this thing. Yeah, you guys see how the string hangs down? Well, okay. It looks like it's going through possibly a few points, either A or C or D. It's like one of those, right? It should always hang through the center of mass. So that place where I randomly happen to clip it isn't super help us narrow it down. But maybe pick like this point right here. Okay. What's it going through? It looks like the closest point is point D. You guys see that? But maybe it's one of the other ones, but it looks like it's going through D, possibly. Okay. Now, this should work from any position. So you just keep rotating it and see what happens. Okay. There it's either B or D. You guys see either B or D? Okay. How about this point right here? Yeah, either D or C. So you guys do see there's only one point it's consistently going through, which is what? Yeah, point D. Let me do one more. Let's try from this corner. See if it also. Yeah, there's A and D. Okay, so point D, it's going through again and again. So next to number 9, write D, because D is the center mass of this thing. Okay. I'll tell you guys a couple other ways you could figure out the center mass. Actually, do one of them right now. It's also the point that it balanced on your finger, right? You guys remember that? So let me do this. I'm going to take this whole foam board, just turn it upside down, and see what point it balances. Now, if I put my finger over here, see how there's going to be a torque? It's going to go this way, or over here, it's torque that way. But let's see. where is it naturally set? It looks like right about there. It's kind of balanced. Right? Now I'm doing the spline. I don't know what's on. Let's see. I hope it's point D. Is it point D?
Yeah.
Oh, look at that. It is. It is point D right there. Exactly it. Or how about this? What if I take this whole foam board and I threw it through the air, and it started spinning, just like spin, spin, spin. Do you guys think it would probably spin around point D? See if that's where it does. You guys have to tell me. Does that kind of work? Sort of?
Yeah.
Oh, it actually did. Okay. Oh, yeah, actually kind of worked, didn't it?
Oh, I can see that.
All right. So, to get what? You've got the rest of class to do this. All the foam boards are in that lab table. Just goes to Great Day where you guys pick up. Also, I do not have access to my grade book yet, so still hang tight on that.